Hi guys, in today's video we're going to be discussing transverse and longitudinal waves. So the first scenario goes as follows. It says a transverse wave moving right is given below with a period of 0.2 seconds. So before we answer the questions, I just want us to define what a transverse wave is. I want us to pay attention to the blue wave. The blue wave is a transverse wave, and the dotted line is the equilibrium. So I want us to pay attention to that red dot. That red dot is a particle on the wave. And if you can pay attention to its movement, you can see it's moving in an upward, downward position. But then if you look at the blue line, you can see that it's moving from left to right. So when the movement of the particle is in a direction that's perpendicular to the movement of the wave itself, then we say the wave is a transverse wave. So the first question says, define the term frequency. So to define the term frequency, I want us to imagine a fixed point on the equilibrium, call it x. So what the frequency is the frequency is the number of complete wave cycles. It's the number of complete waves that passes this fixed point in a given second. Remember, the wave is in constant motion. It's moving from left to right. So the number of complete waves that passes this fixed point in 1 second is called the frequency of the wave. So moving on to the next question. Two pairs of points which are in phase. So I want us to discuss what it means when they say 2 points are in phase. So let's pick a random pair of points. Let's say B and F. So now we want to figure out, is B and F, are these 2 points in phase? So for points on a wave to be in phase, it means that they have to assume the exact same position on the wave. So you can see in the case of B and F, both points are on the crest and they lead towards a downward disturbance. So we say these 2 points are in phase. But the question wants us to find 2 pairs of points. We only found 1 pair. If you consider A and D, you can see that A and D assume the exact same position on the waveform, and they both lead to an upward disturbance. So we can say, therefore, the points that are in phase is points B and F and A and D. A and D. These points are in phase. Now, what about, for example, E and F? E and F are not in phase because E lies on the equilibrium and it leads towards a downward disturbance, and F lies on the crest. It also leads to a downward disturbance, but their positions don't correspond on the waveform. If E was here, it would have been a different scenario. So the only 2 pairs of points that are in phase is B and F and A and D. So the next question says, write down the amplitude of the wave. Now the amplitude is defined as the maximum displacement a particle can assume from the equilibrium position. So let's take a point on the equilibrium, this point here. You can see that the maximum position from the equilibrium is called the amplitude. So this here is what we refer to as the amplitude. If we were to take another point and project it downwards to the trough, it's also another maximum position that, or maximum displacement that a point can take with respect to the equilibrium. So this is another amplitude. And the only information they've provided us is this distance, the distance between the crest and the trough. And that distance, if we construct lines, you can see that it constitutes two amplitudes. So we can say two amplitudes is equals to 30 centimeters. So therefore, if we divide throughout by 2, you can see that the amplitude is 15 centimeters. So the next question wants us to calculate the frequency of the wave. So there's a formula that can help us to find the frequency, and the frequency is equals to 1 over the period, and we are provided with a period which is 0.2 seconds. So therefore the frequency is equals to 1 divided by 0.2, which is equals to 5 hertz. So the frequency is 5 hertz. So the next question says we must find the speed of the wave if the distance d is equals to 3 meters. So we can just note the distance here as 3 meters. So to find the speed of the wave, we can use the universal wave equation, which is lambda multiplied by the frequency. But for now, we don't have the wavelength. We have to find the wavelength, and we have found the frequency already. So let's see with the information provided, this distance, can we find the wavelength? Now, what is wavelength by definition? Wavelength is the total distance between two consecutive points that are in phase. So if you consider this point here, B, and you consider this point here, these 2 points are consecutive points and they are in phase. So this distance here is called the wavelength. And if you consider this point and point F, there are 2 consecutive points and they are in phase because they both are points on the crest. So these 2 points constitute another wavelength. So in essence, you can see that 2 wavelengths, 3 meters lie between 2 wavelengths. So we can find the wavelength. So we can say that 2 wavelengths constitute d. Therefore, 2 lambda is equals to 3 meters. This implies that lambda is equals to 1,5 meters. So now we have both the frequency and the wavelength. So now we can use the wave equation. So lambda is 1,5 multiplied by the frequency, which is 5 hertz. This gives us 7,5 meters per second. So moving on to the next question, it says a tuning fork with a frequency of 100 hertz creates a sound wave as illustrated in the sketch below. So The sketch below represents a longitudinal wave. Let's quickly dive into the definition of a longitudinal wave. So on the schematic, you can see that the longitudinal wave is represented by the orange wave, and the equilibrium position is the dotted line. The red line represents a particle. So you can see the particle vibrates left and then it vibrates right. So the vibration of the particle is parallel to the movement of the wave itself. You can see the movement of the wave, the orange part goes from left to right. So if the movement of the particle is in parallel with the movement of the wave itself, we say that the wave is a longitudinal wave. So let's go to the first question. It says define a longitudinal wave. So a longitudinal wave is a wave where the direction of the vibration of a particle is parallel to the direction of the movement of the wave itself. So that is the definition of a longitudinal wave. So the next question says, name the parts R and S. So on a longitudinal wave, where the coils or the particles are compacted, they are squashed together, this point is referred to as a compression. Compression. And where they are spread out, this is called a rarefaction. A rarefaction. So a longitudinal wave constitutes of parts where the particles are compressed and parts where the particles are spread out. Where they spread out is called a rarefaction. So the next question says, calculate the period of the sound wave produced by the fork. So we've been given the frequency, and using the frequency we are able to find the period. Remember, all the formulae that apply to the transverse wave also apply to the longitudinal wave. So we can find the period. The period is equals to 1 over the frequency, which is equals to 1 over 100, which is equals to 0.01 seconds. Thanks for watching. See you in the next one.